Swayam Prabha. Digital India. Educated India.
Let us consider power in AC circuit. Okay. So now consider a general case where the phase difference between the voltage and the current is phi. So suppose some voltage and the current are having a phase difference of phi. Very general case. It can be lagging or leading, doesn't matter. That sign we can see later. So voltage and the current. Okay. Now suppose we represent this quantity in terms of sinusoidal form. So V is nothing but Vm sine omega t, and I is nothing but omega t minus phi in this particular. If we try to consider the power in the AC circuit, we can have the power is nothing but V into I, the instantaneous power, right? So we can write it as Vm sine omega t into Im, okay, sine omega t minus phi. Is it correct? So Vm Im sine omega t into sine of omega t minus phi. So we can have this expansion as sine a minus b. So this we can write as Vm Im sine omega t into sine a minus b is sine a cos b minus cos a sine b. So we can write it as sine omega t. We can write it as sine omega t cos phi minus cos of omega t sine phi. If you multiply and solve, we can get as, and keeping V as Vm by root 2 and I, which is RMS value, as Im by root 2, and then solving this, we can get this as Vi cos of phi into 2 sine square theta. Okay, so this is some term minus Vi cos phi, not cos phi, here we'll get a sine phi terms. So now substituting these two values and solving it, we can get it as Vi, okay, cos phi 2 sine square omega t minus Vi sine phi 2 sine omega t cos omega t. Okay, so we can write it as like Vi cos phi 1 minus cos of 2 theta. Oh, sorry, I don't know why this theta is coming. Trigonometry, if you apply, you can write is 2 sine square omega t as 1 minus cos of 2 omega t. Okay, minus Vi sine phi, and this term will be nothing but sine of 2 omega t. Correct. And if you see clearly, we can recognize one fact, that this is the instantaneous power. Okay, this is the instantaneous power where this term is going to be positive. always with respective of the t or omega t. This value will be always less than or equal to 1. So this term is positive and this v and I cos phi is positive. So this is always positive. And vi sin phi sin to omega t can be negative or positive depending upon the value of sine. So now if we try to calculate the average power, what's the average power? The average power is nothing but instantaneous power between 0 to 2 pi. So if we take an average power over the interval of pi, just do it. So if you do all kind of calculation from the above expression p is equal to vi, so there is some mathematics involved. You can try this and find out. It will be vi cos phi, which is very important. This average power, or v can be represented capital P. So we'll be writing as capital P. So the capital P is the average power, which is vi cos phi. Okay. And then the average value of the term over a complete one cycle is 0. The quantity vi sin phi is called the reactive power. Okay. So then some quantity which will appear as vi sin phi, right, which is represented as q. So this is basically the reactive power. And this is the active power. Because if you see, there is like two terms, one v, and if you see I is here, I, so this is I cos phi. This is the I sin phi component. The P average active power is nothing but v in I cos phi, which is in the same phase, and I sin phi will be which is in the 90-degree phase shift. This is basically 90. So vi is nothing but volt amperes unit. This is volt, this is ampere, and then we have when P, which is vi cos phi, it is known as watt, W, represented as watts. Okay, and the Q is nothing but kVAR, volt ampere reactive. This is also a kind of quantity which is measured in volt ampere reactives, or okay, so volt ampere reactive. And the total power, which is we can write from here like, so this is basically the P Q, and then P plus JQ. So P plus JQ is nothing but S. This is just a representation where S is the apparent power. Okay, so S is basically the apparent power, and the basically the Q is representing the power which is getting exchanged between the inductive and the capacitive reactances. Correct. So the net power is reactive volt amperes for inductive element minus the reactive component in the capacitive element, and the difference between that will be the Q. Okay. So these are the quantities where the cos phi is known as the power factor. So from here onwards, if something comes up as the power factor, okay, because this is a very important quantity in the power engineering. So power factor is defined as the active power divided by the apparent power. Active power divided by apparent power, which is nothing but Vi cos phi divided by Vi, which is nothing but cos phi. So this is the power factor, which is simply the cosine of the phase difference between voltage and the current. Then AC circuit in which the current lags behind the voltage is said to be having a lagging power factor. Okay, and the circuit in which the phi is leading or the current is leading to the voltage is known as the leading power factor. So basically, so if we remember kind of R, and then we have X, C, XL, then it was something like XL minus XC, and then we used to have this Z, right? So this net phi, the cos phi will be nothing but the R by Z. From the phasor diagram we can see that R by Z is cosine of this angle, which is a power factor angle. Now if you see clearly, for pure resistive circuit, we started with right pure resistive circuit. What is your idea about this phi? If it is a pure resistive circuit, it means that pure resistive circuit means Z is equal to R. It means phi equal to 0, which implies power factor or PF is nothing but cos 0, 1. Now second term, pure inductor circuit. Sorry, pure inductor circuit, what we'll see? Phi is basically 90 degree. Okay. So which implies power factor how much? Cos of 90, which is 0. Similarly, for pure capacitive circuit, phi is minus 90, correct? Which implies power factor is nothing but cos of minus 90, which is cos of 90, which is again 0, not degree, sorry. Yeah. So this is the main, and it's a kind of very important parameter throughout this circuit, and the machine analysis also be seeing the power angle. So the power factor for a pure resistive circuit is unity. For inductive circuit it is 0, and for capacitive circuits also it is 0. So when we talk about the complex power, right, so the S is known as the, here also we have defined, right, S is known as the apparent power. So the power angle, if we represent in terms of power triangle, so S is nothing but P plus JQ, which is definition of P and Q. So this we can have clearly look and understand the effect of different components on the behavior of AC voltage and the current, suppose R, L or C. So depending upon their nature and the difference XL minus XC, the circuit can behave as a capacitive circuit or inductive circuit, and then the phase angle will depend upon the phase difference between voltage and the current. So that will decide the lagging or leading. So dear students, we have so far covered topics such as DC circuits. Then we have seen RLC, series and parallel combinations. Then we have seen along with that this star delta conversion, and then one of the important topic recently we have covered is single phase AC circuit. Okay, so before going to the detail of methods or the techniques for solving the circuit networks, let us consider few examples to understand how we have to do some calculations in case of single phase AC circuit. And this forms a complete circuit. We have a AC source here. So the supply is rated, suppose 230 volt, angle 0 and 50 hertz. So even if the angle is not given, then it is also assumed to be 0, otherwise the angle will be specified with the source. And this is R1, L1, R2, L2, R3 and C. So suppose this value is given as 5 ohm, this is 0.01 Henry, 7 ohm, 0.015 Henry, 12 ohm, 180 microfarad. So these are the values which is given. So in the given circuit, find the following. First, overall power factor. The total power or apparent power. You can write it as a complex power basically. Then active and reactive power component. Okay. This is nothing but the volt amperes. Then active and reactive power. So we have to find these quantities. So if you look at the circuit, we can assume the branches as this quantity, this representation. Suppose this is Z1, this branch represent as Z2, and similarly this branch represent as Z3. So from here, if you just try to find out the total impedance Z, so Z is basically the total impedance seen from this point between terminal A and B. Okay, so Z is nothing but Z1 plus Z2 parallel combination of Z3. So if we solve this, it is nothing but Z1 plus Z2 Z3 by Z1 plus, sorry, this is Z2 plus Z3. Okay, and the total current I will nothing but be by Z. Okay, so I is the current which is supplied by the source, and suppose the current here is branch I1 and here in this branch is. Now with these following assumptions, we will try to look into the circuit part. Okay, so before going to this circuit analysis, let us recall the inductive capacitance or inductive reactance. So just recall the inductive reactance. It's given as XL, which is nothing but the omega L, and capacitive reactance is given as xc, which is 1 by omega c, where omega is nothing but 2 pi f. So in the given circuit example, f is given as 50 hertz, so we have 2 pi into 50, which is nothing but 340. So for this question, the omega is 340. Now let us calculate the Z1. The total impedance Z1 is nothing but the resistance, which is R1 plus J of omega L1, which is XL, the inductive reactance. So this is nothing but 5 plus J of 314 into 0.01, which is nothing but 5 plus J of 3.14. And if you write it in the polar form, it will be 5.9 angle of, it is coming around 32.13 degree. Similarly, if you try to calculate the Z2, it is nothing but R2 plus J omega L2. So if you put the values of omega and L2 in this expression, you will get the value of Z2, the impedance in the branch. It will be around 7 plus J of 4.71. Okay, it will come around 8.437 angle of 33.94, or we can assume is 33.9 degree. Okay. Similarly, if we calculate Z3, it is R3 minus J by omega c. Okay, so here 12 minus J by 314 into 180 into 10 to the power minus 6. Okay, if you solve this, you get 12 minus J of 17.68. The same values in the polar form, we can write it as 21.37 angle of minus 55.83. So these are the values of Z1, Z2 and Z3. Now the total impedance which is being offered between the terminal A and B. So in this case, if we try to find out the total impedance, which is given as Z1 plus Z2 plus Z3. Now substituting these values, whatever we have calculated, so Z1 is 5 plus say 3.14 plus Z2 Z3 product, we'll do it in polar form, so we'll write it 8.4 33.9 degrees is multiplied by divided by sum of Z2 Z3 is okay. Now if you solve this, the total value of Z will turn out to be 12.66 J of 4.82. 4.82. If you write it in the polar form, you get it as 13.54 angle of 20.85. So we have calculated Z. Now what is the total current? What is the total current which is supplied by this source? I is nothing but V by Z. So here in this case, if you see, the voltage is divided by the Z is coming out to be 15.87, or first write it in the polar form, it will be 16.99 angle of minus 20.85, and if you write it rectangular form, it will be 15.87 minus J of 6.05. So we have calculated the current I, which is coming out to be 16.99 angle of minus 20.85. What does it mean? The voltage reference of 230 angle 0, the current is lagging. Okay, so this is your phi, nothing but 20.85. The magnitude is 16.99, so this is 16.9. Okay, so here phi is your 20.85. Okay, so now the overall power factor is nothing but cos of phi. And if you calculate it, it is 0.934, 0.934. Okay, so now the total volt ampere is nothing but V into I. So V is nothing but 230 volt, and I is nothing but 16.9. So this is total 3907.7 volt ampere. Okay, so this is basically the S. Okay, now what is the active power? Active power is nothing but P, which is S cos phi. S is your VI, so 230, sorry, S is your VI, which is 3907.7 into cos of phi is 0.934. This is around 3651.7 watt, and the reactive power Q is calculated as S of sin phi. This 3907.7 into sine of 20.85, which is nothing but 1390.8 volt ampere reactive. So you have to pay attention in the units also. For S, the unit is volt ampere. For P, the active power, the unit is watt. For the value of Q, if you want to have, the unit is a reactive, volt ampere reactive. So this is how you can calculate the total power as. There is another method, alternative method. When you want to calculate the total apparent power S, it is nothing but voltage phasor into the current complex conjugate quantity. So we have two complex quantities, V and I. So now there is nothing but 230 angle of 0 into current is 16.99 angle of minus 20.85. 85. What will happen when we take the complex conjugate? It will be positive. Now if you want to solve it, you may get it as 3907.7 angle of 20.85, and if you write it in the rectangular form, it will be 3651.8 plus J of 1390.8. Okay, so now if you compare the S with P plus JQ, from here you can find P as 3651.8 and Q as 1390.8 volt ampere reactive watt, and this S is nothing but volt amp. So this is another method by which, using this identity, you can find the total volt amperes. Similarly, just extend this problem further. If you want to find out the current I1, so let us find out the current I1. So when you find out the current I1, it is nothing but the, so basically we'll apply the current division rule. I1 is nothing but the total current into the opposite branch impedance divided by similarly I2 is nothing but the total current, opposite branch is Z2 by Z2 plus Z3. So this is how you have to find the I1 and I2. So if you want to calculate the value of I1, is the applying the current division rule. So alternate way, if you want to find out, you can find out the voltage drop between the branch A and B, the small a and B. Okay. So if we apply the KVL in the loop, so go back to the circuit and have a look. If we apply, suppose we give as a C and this is a D, and apply KVL, the bigger loop, we can just name it as A, B, C, D and K. We can write it as, just write the KVL, B minus E B C minus B C D is nothing but 0. So V B C nothing but, we can write it either V C D nothing but V minus V B C, but V minus I Z1, V B C is nothing but I into Z1. Just substitute the values. And if we solve this, we are getting the value as 133.15 angle of minus 8.46. This is VCD. So VCD is basically the drop across the branches Z2 and Z3. Now from here, you can find out using Ohm's law. I1 is nothing but VCD by Z2, which is nothing but 133.15 by Z2, 8.437, angle of 33.9, and here the angle is minus 8.46. So if we solve this, the current I1 will coming out to be 15.78, angle of minus 42.4 degrees. This is using Ohm's law, the drop across. Similarly, the value of I2 can be calculated as VCD, the drop, divided by Z3. So if you calculate this as same base, minus 8.46 divided by the impedance Z3, which is 20.37, angle of minus 55.83 degrees, which is coming out to be 6.23, angle of 47.37 degrees. So now you have I1 and I2. Okay, just check the identity. I is equal to I1 plus I2 or not. So find the I from here. Adding these two, 15.78, angle of minus 42.4 plus 6.23, angle of 47.37. If you add these two values, we will get. So what you have to do, you have to convert these first to rectangular form. So let us do that. So this will be 11.65 minus j of 10.64 plus 4.22 plus j of 4.6, 4.58, and then if you add these two, it will be 15.87 minus j of 6.206, is nothing but 16.99, angle of minus 20.85. So which satisfies the KCL at the node C. So this is how we are going to solve this circuit. So we have found out the I1 and I2. You can again find out the I1 I2 using the current division rule, which I haven't told here. So this is also one method by which you can find the I1 I2, and this is also one method where you just find out the voltage across that branch and then solve it by using Ohm's law. And you can check the identities also, like I1 and I2. So this is how we are going to solve this circuit for AC single phase.